Hi Engineering Janta, I am Vaibhav Shukla and I welcome you all to the third part of the recursion where you learn about time complexity of recursive functions. This is another video in the free DSA series that we are building so that you reach the place where you want to. So, before diving in deep, we'll do our daily ritual. Go ahead, follow these social media handles so that you never miss a hiring update. Also, top 3 comments today get Prep Insta Prime subscription for free. So do not miss that chance of yours. Go ahead and comment below this video. Now, we'll start from the first program that we learned hands-on in the recursion, which was Factorial. Those who haven't watched the earlier videos in recursion, go ahead, watch recursion part 1. You'll understand this particular program there. Okay. So, talking about this particular program, what we'll do today is we'll try and compute its time complexity. Okay. So what exactly we are trying to do? Say that you pass some n number to it. Okay. So what time it would take in terms of the input. Okay. I have explained what time complexity means in the earlier videos. If you haven't checked them out, go ahead, check them out. So say that we are trying to compute the time complexity T of n. Okay. Now if you move ahead and see this particular portion n into factorial n minus 1, this particular portion of this statement would take some constant time, say k1, because this is a simple multiplication operation, so this would take some constant time. This is again a recursive call to this function only, so we can say that this would get solved in T of n minus 1, is it? Now returning 1 is another constant operation, so this would be solved in another constant time, say k2. Okay. So what if I add all of them, what T of n becomes? T of n becomes T of n minus 1 plus k1 plus k2. Okay. What I'll do is I'll combine these constants. Okay. And I'll write k equals to k1 plus, just a minute, equals to k1 plus k2. Okay. Wherever you find k1 plus k2, replace it with a single capital K. Okay. So T of n, I'll draw a line for the further computation. You'll understand why I've drawn it. So T of n equals to k, a bigger K for them, plus T of n minus 1, right? Now if I go ahead and try to compute this is basically a recurrence relation that we have written. This method that I am teaching you is called as recurrence relation method to solve time complexities. At some places this method won't work. There I would teach you another method in this video only, which is recursion tree method. So first of all we'll learn this one. Okay. So if I try and compute T of n minus 1, कैसे निकालें इसको? Again a similar pattern can be formed for this. What I do is k plus T of n minus 2. How do I get this n minus 2? N minus 1 minus 1. So minus 1 and minus 1 becomes minus 2. What I just said was n minus 1 minus 1 equals to n minus 2. Okay. This is what I just did here. I just substituted n minus 1 at the place of n, and what we got is n minus 2. Simple. Now for T of n minus 2, what we do is k plus T of n minus 3, T of n minus 3 equals to k plus T of n minus 4. This is quite simple, going in the similar fashion. And now this would go on till T of 1, which is nothing but 1, or I would say kth operation, which is k2 operation, I would say. Why so? As soon as you get 1, 1 is not greater than 1. So this block won't execute. This else block would execute. As soon as it executes, the recursion stops. Okay. So this particular operation is being done in k2 time. So this k2 time is written here. Very simple till now. What now we'll do is we add all of them. We'll add all these terms. What we'll get is the total time complexity. So when you try adding them, what you get here is you'll actually cut them out, right? When you add them here and you add them here, on both sides of equal to, these similar terms would be cut, right? So in this fashion, this would go on, and T of 1 would also be cut here somewhere. Okay. So using this, what we actually get is T of n here, and just before T of 1, there would be n minus 1 terms before T of 1, because till T of 1 there are n terms. So before it, there would be n minus 1 terms. For those n minus 1 terms, this k is repeating, right? So what I'll do is k into n minus 1 plus k2, right? So this k2 is some constant, which is smaller constant, so this can be ignored. I'll ignore it simply. What I'll say is kn minus k. Again, I can ignore this constant, so which is k of n. So the total time complexity, if I check for this, is of order of n, because the function T of n, which was the total time complexity for this code piece, is actually in the order of n. We have just checked. K of n is the basic term that we were reduced to this, right? So when we reduce to this, what we are achieving? Order of n. So this is the time complexity for factorial. When we try and build a program for factorial using recursion, we get linear time complexity. We get order of n. This is very, very simple, right? But if you have watched the last video, I told you recursion is not preferred in the Fibonacci sequence. Now, I'll tell you how to compute the time complexity for Fibonacci sequence, and you will see why it is not preferred. Okay? So we'll move ahead. So this is the Fibonacci sequence for which we are trying to calculate time complexity. Now if we see and say that for this particular portion, T of n is the time complexity that we need to compute, right? So if you check here in this if block, there is only one return statement that is being executed, which would take some constant time. Say it takes k1 time, right? When we check this else portion, we have two recursive calls for the same function. So basically, if this is taking T of n time, this would take T of n minus 1 time. Similarly for this, it would take T of n minus 2 times, right? Just a minute, I'll make this T better for you. Okay. And this plus portion, this arithmetic operation that is happening here would take again some constant time, say k2. So again in this, what I try and do is, I add this k1 plus k2 here itself, because you will see addition happening further, and I say that capital K denotes the sum of these two constants. Okay. Now we try writing using recurrence relation that how its time complexity can be calculated. Okay. So if we write T of n, then it becomes k plus T of n minus 1 and T of n minus 2, right? So this is how it would look like. Very simple. Now, if we try and compute T of n minus 1, what do we get? We get T of n minus 2 in the similar pattern followed above, and T of n minus 3. If we try and compute T of n minus 2, what do we get? K plus T of n minus 3 plus T of n minus 4. If we try and compute T of n minus 3, what we get is K plus T of n minus 4 plus T of n minus 5. How are we getting this? Using this particular recurrence relation, we are trying and substituting every time, just as we did it in factorial example. Okay. So if it goes on, it would go like this somewhere. When we reach T of 1, this portion would execute. So basically k1 time would be taken. Then it would go to T of 0, and again k1 time would be taken. Simple. So for this extent, if I try and add them up, what I get is, I can, if I try and do the sum of them, I'll cancel these terms out, right? I'll cancel these terms out every time. Somewhere they would be cut, but this whole chain of terms would remain. This whole chain of terms would remain, and it is super complicated to check them, to compute them, Here itself, it is very, very complicated. So there is another faster method for it. How do we calculate it? I'll tell you. You form a recursion tree for the Fibonacci sequence function that we used. What you do is, for the first term, if it is n, it would split into n minus 1 and n minus 2. We just saw that, right? For n minus 1, it would split into n minus 2 and n minus 3, right? For n minus 2, it would split in n minus 3 and n minus 4. Then for this, n minus 3, n minus 4. For this, n minus 4, n minus 5, n minus 4, n minus 5. For this, n minus 5 and n minus 6. Then if we go ahead, again 2 child nodes would be there for each node, right? So basically what I'm trying to explain you is, it would go until we have, for some n term, for some nth time, we have a value where this function would completely get computed, right? So how do we calculate that? Very simple. If I'm trying to calculate the time complexity using this method, basically the time taken by one node can be assumed as k. Say that one node takes k time to execute. Okay. So if there are some number of nodes which I can calculate, if I can calculate that, what I can do to calculate total time complexity is number of nodes into k. If I'm saying that one node, each node takes k time to execute, then if I compute total number of nodes and I multiply it with k, I'll get the total time complexity. Simple mathematics. What I'll try and do here is, I'll try to calculate these number of nodes. At every step, if you carefully check, what's happening is, here you are getting one node, right? At this step, you're getting two nodes. At this step, 4. At this step, 8, and then 16, and then so on, so on, so on. So say for the last step, I would get 2 raised to power n nodes. Basically, why am I getting it? If you see 2's power 0, 2's power 1, 2's power 2, 2's power 3, 2's power 4. That's how it is going ahead. So what do we get here is, the total number of nodes, if I try and add at each step, we would get 1, I'll write here, total nodes equals to 1 plus 2 plus 4 plus, if you see 8, 16, it is going on like this till some number, right? So we can say that till 2's power n this is going on. What we'll do here is 2's power 0 plus 2's power 1 plus 2's power 2 plus 2's power 3. I'll write it in these terms till 2's power n. Okay. If you go ahead and check that what is the sum for this series, this is taught in class 11th and 12th. So this particular sum is actually 2's power n plus 1 minus 1. This is how the sum for this particular series looks like. Okay. This is something you have to remember if you haven't studied it earlier in class 11th or 12th. Okay. Now, if I try and multiply it with this particular k, then what I'll get is my time complexity. So I'll go ahead, multiply this. Okay. If I multiply this, what I get is 2's power n plus 1 into k, right, minus k. So this minus k can be easily neglected, isn't it? Why it can be easily neglected? It is a small constant, I can neglect it. So I let go of it. What I'll get is 2's power n plus 1 into k. This is actually into, okay. So when you try and build this kind of function, what you basically get is, we can go ahead one step further and can write this as 2n into 2k. Basically, we just separate this 2's power 1 from the 2's power n. Okay. So we separate it and what we get is 2's power n into 2k. So this is again some constant. What I'll do is I'll neglect this constant as well. As soon as I neglect it, what we get is 2's power n, which is basically the time complexity. So this is order of 2 raised to power n, which is nothing but an exponential function. That is why it is not preferred. Whenever we check it, whenever we say that we are trying to write Fibonacci sequence, the last method preferred is recursion, because here if you check, the order that you are getting in the time complexity is 2 raised to power n, which is exponential time. So you never prefer exponential time. This is a very bad time complexity. If you have watched my time complexity video, you will see the particular order of growth, how it actually looks like from best to worst time complexity. Okay, so this is not a very good time complexity, but that's how actually you calculate the time complexity using recursion trees. Okay, so these are two primary methods using which you can calculate the time complexity for recursive functions. That's all for today, and before we wrap up, you go ahead, follow us on Instagram and various social media handles so that you never miss a hiring update. And top 3 comments get Prep Insta Prime for free, so that is a golden chance you must not miss. And whatever knowledge you get, keep spreading it. Keep doing good. Good will come back to you. You just keep doing good for people without any expectation. Things will happen in a wonderful manner for you. That's all for today. Thank you.